At this point, you have learned that two functions that are inverses of each other have graphs that reflect each other across the line y equals x. However, we need an algebraic or an analytic method for really proving that two functions are inverses. In 5.1.5, we will examine this analytic method for verifying inverses. Definition: let f of x be a one-to-one function. Then f inverse of x is the inverse function of f of x if, all right, you ready for this? F composed with f inverse of x equals x and f inverse of f of x equals x. This is our algebraic or analytic test that we can use to prove that two functions are inverse functions. First of all, notice we are back to finding the composition of two functions. The little circle is the symbol for the composition operation. Recall that is when we plug one function into another function, or you can think of it as evaluating two functions successively. Also notice that these two operations appear to be commutative. That is, I can apply this composition in either order and get x each time. In general, we learned that composition is not commutative. That is, if I switch the two functions in order in the composition, we generally get something different. But if we are dealing with inverse functions, then their composition will always turn out to be x. Now, let's go back to the very beginning of our notes when we drew a mapping of the relationship between a function and its inverse to understand how this actually works. Let's consider f inverse of f of x, y that is equal to x. Now, f inverse of f of x can be written f inverse of f of x, right? So we have an outside function and we have an inside function. If I want to evaluate f of x, I'm going to have some sort of input. So we'll say this is the input to the function. Then I'm going to apply an operation to it. When I apply this operation f, I get some sort of output over here in the range of f. We're calling that f of x. Then, once I complete that operation, I'm immediately going to apply the inverse function. So if from this point in the range, I immediately apply the inverse function, guess what? I end up right back where I started. So the input to the function is the same as the output. Thus, f inverse of f of x will always equal to x. Those two functions, when applied successively, are reversing the action of each other. So the argument is preserved. Let's see how this plays out in example 6. Example 6 says, using composition, not a graph, determine if f and g are inverses of each other. So we're going to apply this algebraic test. That means we're going to compose our two functions in both orders and see if we get x. This is a great opportunity to review composition of two functions. F composed with g of x can be written in terms of the two individual functions as f of g of x. Now, remember, to execute this, we postpone the operation represented by that outside function until step 2, and then we're going to replace g of x with its function rule. Notice over here, g of x is equal to 1/2 x minus 2. So I'm going to take that function rule and replace g of x. We get 1/2 x minus 2. Once that's complete, then we're going to apply f to this new argument. So I can see that this new argument here is in the belly of f. So I'm going to go to the function called f. I'm going to find the variable, and I'm going to put this argument in place of that variable. This is going to give us 2 times the quantity, 1/2 x minus 2 plus 4. So the original function is 2 times something plus 4, and notice here we have 2 times our new argument plus 4. So again, we're just reviewing composition. Let's use our distributive property to break up these parentheses. 2 times 1/2 x is x. 2 times -2 is -4. We have a plus 4 out here on the end, so notice when we simplify, we end up with x. So in this forward direction, it appears that we are working with inverse functions, but our proof is not complete unless we can reverse that order and prove that we get the same result. So this time, g is going to be on the outside and f is going to be on the inside. So I'm going to postpone g to step 2, and I'm going to replace f of x with its function rule, which is 2x plus 4. Then interpreting the coded instructions here, this says go to the function called g, so I know I'm going to be using this rule, and I'm going to plug in the argument 2x plus 4. That is, where I see that x, I'm going to put the 2x plus 4 in that box. So this becomes 1/2 times 2x plus 4 minus 2. Applying our distributive property, 1/2 times 2x is x, and 1/2 times 4 is 2. And then notice the 2 minus 2 cancels, and we get x. We can say, therefore, by the way, these 3 little dots mean therefore, f and g are in fact inverses. If I were to graph those two functions, I would see that they are reflections of each other across the line y equals x. All right, let's try that again. Again, it's great practice with the operation called composition. We've got, let me say one more thing about this. Notice in the first function here, we were multiplying by 2. Here we are dividing by 2. In the first function, we are adding 4. Well, where is the minus 4? If I were to get a common denominator between these two and rewrite the function with a common denominator, it would look something like this. So this is equivalent to this one with combined fractions, and then you can see there's the minus 4. Okay? Now, let's look at this new f and g. We're going to evaluate the forward direction, f composed with g of x. This means f is on the outside, g is on the inside. So I'm going to replace the function g of x with its function rule, which is 1/4 x plus 1. Then we're going to take that and plug it into the function called f, where we see the argument x, or putting 1/4 x plus 1 in that box. With our distributive property, we end up with 4 times 1/4, which is 1x, plus 4 minus 1. When we simplify, we end up with x plus 3. Notice that is not what I'm looking for. I don't want to force it to be x. I want to prove that naturally, if it's inverses, we will end up with x. Because we did not get x, we are done with the problem. So it's kind of nice when they're not inverses. You only have to do one direction of composition. We can say f and g are not inverses. No need to show the other direction, g composed with f, because in order to be inverse functions, f composed with g and g composed with f both have to be equal to x. If one direction fails, you can go ahead and make the conclusion f and g are not inverses. If I graph those two functions, I would see they would not be reflections of each other across that line y equals x. Let's finish out with the last one and begin with your intuition looking at these two functions. Do you think that they will be inverses? Can you see pairs of inverse operations? Notice here we have a cube root. That is the inverse of a cube. Here we have a plus 1. That's the opposite of a minus 1. So it appears that they will be inverses. The question is the order of operations correct? Should it be like this to have inverses, or is it correct as is? So let's find f composed with g of x. This is f on the outside, g on the inside. Replacing g with its function rule, that is x minus 1 cubed, we then plug this new argument into the function called f, where I see the x. So I'm going to plug x minus 1 cubed in for x under that radical, and notice the plus 1 is outside the radical. We have the cube root of x minus 1 cubed. The cube root and the exponent 3 cancel, and we end up with the radicand, and the negative 1 and positive 1 cancel. So it appears that we are dealing with inverse functions on at least this direction. To be complete and thorough, we also have to show that g composed with f of x is equal to x. So let's see what happens on this one. G's on the outside, f is on the inside, so we're going to replace f with its function rule. That is cube root of x plus 1. Be careful, make sure that your radical stops in the right place. Then we're going to plug this into the function g where I see that variable. So this becomes parentheses cube root of x plus 1. Okay, so the cube root of x plus 1 was placed in this box, but we still have a minus 1, and we need to cube. Notice the order of operations here is different. Over here, the cubes canceled first, and then the negative 1 and positive 1 canceled. Over here, notice the minus 1 plus 1 cancels first, and then the cube root of x cubed is x. So the order of operations was the opposite. But because we got x in both instances, we can say therefore. Again, that's just a symbol from math representing therefore. You may have seen it in high school geometry. Therefore, f and g are inverse functions. If I wanted to visualize this, I could graph those two functions and observe they would be reflections of each other across the line y equals x. However, the composition is the most analytic and trustworthy proof, more reliable than a graph.